Great. So I guess we can get started. And as Richard mentioned, we're starting with a tutorial on quantum error correction. So just to kind of motivate why we're even talking about error correction in the first place, as we know, kind of everything we build in the real world is going to have some error rate, some probability of failure. And if we look at, say, like current hardware, so current quantum computers people can build, the error rate is maybe somewhere around 10 to the minus 2 to 10 to the minus 3. And what I mean by that is for every 100, or to every roughly 100 to 1,000 gates or operations you perform on a quantum computer today, you'll have an error. One of your qubits will get corrupted. It's a super rough estimate. I'm not trying to make any real quantitative claims, but just to give an order of magnitude estimate. In comparison, for target applications, so things maybe like Shor's algorithm, if you've heard of that. If you want to, say, crack RSA by factoring some giant numbers, we might want an error rate on the order of something like 10 to the minus 10 to 10 to the minus 15. Again, super rough estimate, just orders of magnitude. But the idea is maybe in this application, we need to run 10 to the 10 to 10 to the 15 gates in succession, and we need all of them to execute successfully, which means our error rate should be roughly the inverse of the number of gates we perform if we want to kind of successfully get the right output. So kind of the goal of quantum error correction is to essentially close the gap between these numbers. It seems somewhat unlikely that with current hardware, we're actually going to get error rates as low as we need for some of these target applications. So instead, we can hope to use quantum error correction, where essentially we can simulate like Shor's algorithm or some algorithm in this target application, and kind of simulate running this algorithm at a very low error rate on much more noisy hardware. Hardware that's maybe has an error rate of 10 to the minus 3 or maybe 10 to the minus 4. But yeah, so kind of quantum error corrections, it's all about using hardware at this level to kind of perform computation at this error rate. And it really seems like it's probably necessary if we ever want to realize the potential of quantum computation. So in this tutorial, I'm going to start off just giving a brief overview of classical error correction. So classical error correction with just kind of the simplest classical code of them all, which is the classical repetition code. And when we try to quantize that, turn it from a classical error correction scheme to a quantum error correction scheme, we're already going to see that some things go wrong. But fortunately, we can fix these things and get to some basic quantum error correction schemes. And specifically, we'll see that something called stabilizer codes are a very useful paradigm for kind of designing quantum error correction schemes. And we'll look at two specific examples. The Shor 9-qubit code, which was one of the earliest quantum error correcting codes discovered, and then the surface code, which is still kind of one of the most popular codes today. Then we'll move on to the question of, so we'll have some kind of abstract scheme for correcting errors, but if we actually want to implement this, we want to kind of store quantum information in a fault-tolerant manner. So do all the error correction in a way that's fault-tolerant on like a physical device. And for fault-tolerant storage, we'll see that something called quantum LDPC codes are very well suited for that task. And then the final topic we'll cover is actually computation. So ultimately, we don't just want to kind of store quantum data. We want to actually perform computation on it. But we can't kind of unencode our data, perform computation, and re-encode it. We always need to be protected against errors while we do the computation. And we're going to see there's some impossibility results, some barriers, but there's also a number of techniques to get around these barriers for computation. So that's basically an outline of where we're going. I will say I released kind of a preliminary document with just some reading materials and some problems in the link that Richard posted. I might update that after the talk, depending on how far we get. But I'll also kind of, most of the problems will come up as exercises during the talk anyways. Okay, great. So we can start with classical error correction. Specifically the repetition code. And the question here is, like, how do we encode classical information such that we can protect it against errors? And so classical information is bits. So if we want to protect it bits against errors, kind of the simplest thing we could possibly do is literally just repeat the bits. So if we have the bit 0, we can repeat it, say, 3 times to 0, 0, 0. And if we have the bit 1, we can repeat it 3 times to 1, 1, 1. And we call this mapping just the encoding map. And then if we have a longer bit string, maybe our message is something like 0, 1, 0, 0, we encode that by just encoding each bit. So we get 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 0, 0. And already you can see it's almost trivial to correct a single error, because say we have like the 1, 1, 1 string, and then we have an error, and maybe the middle bit gets flipped, so we get 1, 0, 1. Then essentially we can just do a majority vote, so we can decode this by running majority vote, and we'll get back 1, 1, 1. Because there's 2 1s and 1 0. So this is great. Classically, at least, we can do some very basic error correction with almost no work at all. And the natural question we want to ask is, how can we quantize this? How can we turn this into a quantum scheme? And actually, this is already quite difficult, and there's like a fundamental problem. There's a fundamental reason that we can't just take this classical scheme and immediately make it quantum. And the problem here is what's called the no cloning theorem. And what this theorem says is that the repetition map that we could use quantumly so easily actually isn't a physically implementable quantum map. So the map that sends the state psi to, say, 2 or even 3 copies of this state psi, this actually turns out to not be a linear map. Which means it's like not physically implementable. In a second, I'll give a brief recap of kind of our notation with quantum mechanics and so forth. But suffice it to say here, we can't even implement this repetition map quantumly. So somehow we should really expect this repetition code to not have a quantum analog. And already this poses a kind of big conceptual challenge for quantum error correction, because it's really hard to see how to protect against errors without storing your information redundantly. You can imagine more complex schemes classically, but it seems like we'll always want to kind of repeat our information across space, so that if any one area of space gets corrupted, we can recover it from somewhere else. And at a high level, the conceptual solution to this problem is actually somewhat subtle. what we're going to do is we're going to find ways to store quantum information. Store quantum information in a manner that's somehow both non-local, so we'll spread our information out across space, and non-redundant. So we're actually not going to repeat our information. We're just going to kind of delocalize it throughout space. And once we delocalize it throughout space, even if kind of any single qubit is corrupted, we'll have our information also stored across other qubits, so we can recover our information from these other qubits, but somehow we still haven't duplicated our information. We've just somehow delocalized it. So that's where we're heading. Before getting into the details of how we actually perform this non-local encoding, I'm going to give a very brief review of just some basics with qubits and so on, basically just to make sure that we all are on the same page with notation and so forth. So if you're familiar, you can probably tune out for the next 5 minutes or so, and then we can get back to error correction. Oh, so as we all know, a bit is the fundamental unit of classical information. And quantumly, that becomes a qubit. So the fundamental unit of quantum information is a qubit, which we'll write as ket of some vector, say phi. And a qubit is actually a two-dimensional complex vector. So it's a linear combination of these two basis vectors, which we write as ket0 and ket1. So these coefficients phi0 and phi1 are in C, they're complex numbers. And this vector lies within C2. So ket0 and ket1 are two basis vectors. Then if we have n bits, so a length n bit string, x1 through xn, in 0, 1 to the n, classically, we just kind of write the bits out in a line. Quantumly, we have an n qubit state, which is actually not simply n qubits written in a line. That would be kind of a 2 times n dimensional vector. Instead, an n qubit state is a 2 to the n dimensional vector. So we'll write it ket psi is a linear combination of some coefficients, psi sub x, again, complex numbers, times ket x over all bit strings x in 0, 1 to the n. So we have a different basis vector for every bit string. And there's 2 to the n bit strings, so we have 2 to the n different basis vectors. And for each one, we can put a complex coefficient in front. So an n qubit quantum state is a 2 to the n dimensional complex vector. Now, finally, we also need to think about kind of performing computation on these states. So classically, we can run circuits, which really just means we apply an arbitrary function to our bits. So it's a function that maps, say, a bit string x to another bit string f of x. That's what we can compute with a classical circuit. Quantumly, we actually can't perform arbitrary circuits on our quantum states. Essentially, we can only perform operations, we can't apply arbitrary functions to our quantum states. We can only perform operations that correspond to unitary operators. And this essentially means we can only perform mappings that take a state psi and map it to u times psi, where u is it's a linear operator, so it's essentially 2 to the n by 2 to the n matrix, 2 to the n by 2 to the n complex matrix. And the unitary condition just means that the complex conjugate of u, so the matrix we get by taking u, taking its transpose, and then taking the complex conjugate of every entry, is equal to u inverse. Or equivalently, u dagger u equals the identity. And so this kind of, when I mentioned we can't clone a quantum state, I'm saying there's no unitary operator. In particular, there's not even a linear operator that performs this cloning map. Great, so the last kind of bit of intro we need before we can get back to error correction is the notion of measurement. And with measurement, again, we have another kind of conceptual difference between classical and quantum, which is that quantumly, we actually can't extract arbitrary information about a state. A quantum state for n qubits is described by these 2 to the n complex coefficients, psi sub x. We can't just read these off if someone hands us the state. We can only perform what's called measurement, where we learn something about these coefficients, but we also perturb the state in the process. And in this tutorial, we're going to restrict attention to actually a specific type of measurement called Pauli measurement. And so Pauli measurements, they're essentially 2 outcome measurements that are a bit simpler than general measurements. That's all we'll need here. So we can briefly recall that the Pauli matrices are, I guess we have the identity matrix. And then we have kind of 3 2x2 matrices called Pauli matrices, which are X, which is 0, 1, 1, 0. Z is 1, negative 1, 0, 0. And Y is I times X times Z, which is I, negative I, 0, 0. And for these 3 X, Y, Z Pauli matrices, you can see that they're anti-commuting. So that basically means that, for instance, xz is negative zx. The same for xy is negative zy, xy is negative xy, and so on. And their eigenvalues are plus or minus 1. This is true for all 3 matrices. And so if we want to measure an arbitrary state psi, we can essentially choose a Pauli p, and we can say we want to measure this Pauli. And that's going to do 2 things. As I mentioned, that's going to give us some measurement outcome. It's going to tell us some information about the state psi, and it's going to collapse the state. It's going to perturb psi and kind of project it down to a subspace. And these 2 things each happen with some probability. So with some probability, we essentially observe +1, and with some probability, we observe -1. And if we observe +1, we collapse the state psi to its projection onto the +1 eigenspace of the Pauli operator p. Whereas if we observe -1, we collapse the state to the projection onto the -1 eigenspace. So by pi p -1, I just mean the projector onto the -1 eigenspace of the Pauli p. And the probability for these 2 events is actually the square of the norm of the collapsed state. So the probability of observing +1 is the square of the norm of the projection onto the +1 eigenspace of p. And the chance of observing -1 is the square of the norm of the projection onto the -1 eigenspace of p. Great, and so just to do, I guess, specify, so we can do this for the Pauli x, or we can do it for the Pauli y, or z. We can also do this measurement for multi-qubit Paulis. So essentially, we can take tensor products of Paulis, meaning we essentially apply different Paulis to different qubits. That will still give us operators that have plus or minus 1 eigenvalues. So we can do the same procedure. So we can measure, for instance, z tensor x, or z tensor x tensor I tensor y. And I just want to say one more thing about this, which is that z measurements we'll actually see a lot today. And these we can think of as kind of parity measurements. So for instance, if we have the state psi that's like a 3-qubit state, say like x1, x2, x3, and this could be something like 1, 0, 1. So x1, x2, x3 are bits. And if we try to measure the Pauli that's like z tensor I, then we see that if we apply the Pauli p to our state psi, what we get back is the same state psi, but with a sign, which is precisely -1 to the x1 plus x2. Essentially because this z will flip the sign if x1 is 1, and this z will flip the sign if x1 is 2. Or sorry, if x2 is 1. And you can see that here because z essentially, if it sees ket 0, if it sees the first basis vector, it does nothing. If it sees ket 1, if it sees the second basis vector, it flips the sign. Which means that if we measure Pauli p on this state, we observe essentially either +1 or -1. +1 if x1 plus x2 is even, and -1 if x1 plus x2 is odd. Sorry, that's a little small. But essentially, our observation tells us the parity of x1 plus x2. And in general, z basis measurements, so if we measure tensor products of Pauli z's, we learn something about the parity of sums of the bits in our computational basis. And that's kind of going to be the key behind a lot of our error correction procedures, is to compute parities by measuring these types of Paulis, and then use these parities to correct errors. Oh. Great, so are there any questions on this? Okay, great. So now we can get back to error correction. And we saw that we have this classical repetition code. It shouldn't work quantumly because of the no cloning theorem. So we're kind of back to square one. And since we don't know what else to do, let's just try to quantize the classical repetition code and see how far we get. So let's try to quantize the repetition code. And we'll see that it kind of works somewhat, but then it fails at some point. And if we can we'll find a way to fix where it fails, and then we'll actually end up getting a real quantum code out of this. So we just have our classical repetition code, and to make it quantum, we can just kind of do the same thing, but to qubits instead of bits. So we can take the 0 qubit and encode it to 0, 0, 0. Take the 1 qubit, encode to 1, 1, 1. And this actually uniquely defines a quantum encoding. Essentially because, as we saw, quantum circuits, quantum unitaries are linear. So for instance, any linear combination like 0 plus 1 over root 2 gets encoded just to a linear combination of 0, 0, 0 and 1, 1, 1. So. And the idea is now if we have an error occur, say a bit flip, so a bit flip error, that will map our state to something that's corrupted. So something like, say we start with 1, 1, 1, then we have a bit flip, we'll get back something like 0, 1, 1, or 1, 0, 1, or 1, 1, 0. And we can ask, like, what exactly is a bit flip error? Well, it's actually precisely an X error. So if we apply Pauli X to the first qubit and identities to the other two, we can see that Pauli X maps it maps the ket 0, the first basis vector, to the second basis vector, and it maps the second basis vector to the first basis vector. So Pauli X just swaps our two basis vectors, which is literally what a bit flip is. So every time we have a Pauli X acting on one of the three qubits, so XII, IXI, or IIX, we get a state that corresponds to our original state with one bit flip. And then we can actually just always decode this back to 111, just using majority vote like we saw classically. So this is just the classical repetition code, but in qubits instead of bits. And this is great, but there is a problem. As we expected, there should be a problem because of the no cloning theorem. And the problem is that there's a second type of error that could occur quantumly called a phase flip error, which essentially means that we apply a Pauli Z instead of a Pauli X to our quantum state. So for instance, if we apply Pauli Z to the first qubit and identities to the other two, then if, say, we start with the code state that's 000 plus 111 over root 2. So we take like this code state, for instance. The error just on the first qubit, we get 000 minus 111 over root 2. And this is actually bad because this is also a code state. We can say that this is a linear combination of our two basis code states. So essentially, we've had an error acting on a single qubit, which maps one code state to another code state. So this is very bad. We've basically corrupted our underlying logical data. If we now try to decode this state, this 000 minus 111, we'll get back something that's different than what we started with. So our classical repetition code has no ability to correct against phase flip errors. Now, it turns out that we can solve this without really going beyond the classical repetition code. We just need to think a little more carefully about what is a Z error. So a phase flip in the standard basis, so by standard basis I just mean the basis we've been working in, where our basis vectors are bit strings in 0, 1 to the n. A phase flip in the standard basis is an application of Pauli Z. But it turns out that we can actually swap to what's called the Hadamard basis and map this phase flip to a bit flip. In the Hadamard basis. So by Hadamard basis, I mean what we get when we take all of our qubits and just apply the Hadamard gate to them, where we'll recall the Hadamard gate, it's just this 2 by 2 matrix, 1, 1, 1, negative 1. So specifically what I mean by this is that if we conjugate Pauli Z by Hadamards, by this matrix here, we get Pauli X. Or Z is equal to H times X times H. Equivalently, HZH equals X. And what this means is kind of if we switch into this Hadamard basis, if we apply the Hadamard gate to all our qubits, then if we had a phase flip occur on our code state, in this basis, this phase flip now looks like a bit flip. So this is suggesting, like, why don't we just encode our message using the repetition code, but in the Hadamard basis. So first switch to the Hadamard basis, do an encoding, and then we'll protect against Z errors. But of course, the problem then is we then won't be protecting against bit flips, against X errors. Essentially, the classical repetition code can only correct against either X errors or Z errors at a given time. Great. So does anyone see a way that we can try to correct against both an X error and a Z error with a single code?
You can use the short code?
Yes, great idea. Oh, yeah, this is exactly where we're going. It's remarkable. And yeah, so I think the short code is short for concatenate two of these repetition codes together. One the standard basis and one the Hadamard basis. So essentially what we want to do here is we take our message, either 0 or 1, and we first just encode in an ordinary repetition code. So I'll write that as 0 tensored with itself 3 times, which is just 0, 0, 0. And we map 1 to 1 tensored with itself 3 times, which is just 1, 1, 1. And then we're going to switch to the Hadamard basis. So we're going to apply Hadamard gates to all 3 qubits. So the idea is that once we protect against bit flips by encoding in this repetition code, we still don't protect against phase flips, so let's just flip to the Hadamard basis, and then again apply another repetition code encoding. So we apply Hadamards. After applying these Hadamards, our state looks like this. 1 gets mapped to 0 plus 1 over root 2, tensored with itself 3 times. 0 gets mapped to that. 1 gets mapped to 0 minus 1 over root 2, tensored with itself 3 times. And then we again encode in a repetition code. So we now just repeat each qubit here 3 times. And what we get is 0, 0, 0 plus 1, 1, 1 over root 2, tensored 3 times. And down here we get 0, 0, 0 minus 1, 1, 1 over root 2, tensored 3 times. And we call this state on top, we'll call it the logical 0 state, or 0 with a bar on top. And we'll call this state on bottom 1 with a bar on top. So essentially, we've concatenated together 2 repetition codes with a basis switch in the middle. And we ended up with kind of, this is a 3-qubit state tensored with itself 3 times. So it's a 9-qubit state. Whereas we started out with just a single qubit. So we have a code that's 3 times as long. And the claim is that now we're going to be able to correct against both bit and phase flips. So I guess are there any questions about this encoding map?
So in the classical case, it's fairly obvious that the bit flips that can happen will happen with the same probability. But why do you know that the phase flips and the bit flips would be, or the quantum case would be the same, would have the same probability? Is there any reason for that?
I see. Why would bit and phase flips have the same probability?
That is why is the Hadamard symmetry preserving the probability of error?
Right. So I'd say for now we won't say anything about actually the probability of a bit or a phase flip. And indeed, actually, often you can have bias noise where bit flips are more likely than phase flips. So what the Hadamard gate is doing, it's basically doing a basis change where it lets you view a bit flip as a phase flip, but it's not actually changing the underlying probability. So if say bit flips are more likely than phase flips, after a Hadamard gate, then now phase flips would be more likely than bit flips. But we will get into error models a little later, at least random noise like that. Yes?
I'm not sure how much error you can get when you encode, but what if you're trying to encode for a Facebook correction and you get a bit flip?
Yes, encode for a phase flip correction, then you get a bit flip. Yeah, so that's a good point.
Or the opposite as well.
Yeah, exactly. Right. So with the short code, the idea is this first encoding encodes us against bit flips. And then we do a Hadamard gate and do a second encoding. And this encoding is meant to protect us against phase flips. So actually the thing that we'll see next is that essentially when we combine these two encodings and we just view the entire map from this single qubit to these 9 qubits, this is actually encoding us against both a bit flip and a phase flip.
So like in the first process of encoding against a bit flip, what if you get a phase flip?
Oh, you mean like if we get it? Oh, yes. Yeah, sorry. Oh, this is a great point. We'll get there maybe in the second half. This is like a really important point. Yeah, this is not like fault tolerant. Exactly, yeah. So if errors happen here, we're screwed. Yes.
What's like the computational complexity of encoding into the shortcode or decoding?
I see. So I guess it depends how you measure complexity. One option is to like measure gates or something, like the number of gates you need. You can write down a circuit. For instance, this encoding map is essentially 3 C0 gates. It's something like we start with zero, like ancillary zeros, and then our original state, phi. And then we just do a couple of C0 gates. So we need, I guess, 2 gates to do this encoding. Then we need 3 Hadamard gates. And then we need 3 more copies of this circuit. But actually, the last question was saying that kind of this is actually not how we're going to want to encode in practice, because if a phase flip happens here, we're already screwed. So I don't know if we'll get to state preparation in this tutorial, but it actually can often be a tricky question to figure out like the best way to prepare a code state. Yeah, it's definitely not an easy thing to do. Oh, great. So if there's no more questions, we can briefly see how the shortcode can correct against a bit flip error. So bit flip or an X error. So this will essentially take, say we start in the logical 0 state over root 2, tensored with itself 3 times. Say we apply a bit flip to the first qubit. So I'll write that as x1, and that just means x tensored with a bunch of identities. So we just flip this qubit. What we get out is 1, 0, 0 plus 0, 1, 1 over root 2, and then tensored with 2 copies of the original state. So these things are uncorrupted. The only thing we've corrupted is we've corrupted the first part to this state. And the key point is if we just look within the first part and apply our majority vote decoding, we can essentially this is just decoding a classical repetition code. And so we can decode against this bit flip, essentially because we have 3 copies of a repetition code from this encoding. So we can still protect against bit flips. Just erase this. If we have a phase flip, or a Z error, then we start with the same initial state. Won't write out the whole thing. Now say we apply a Z, Pauli Z to the first qubit. What we end up with is 0, 0, 0, minus 1, 1, 1 over root 2, tensored with 2 copies of the original state. So 2 copies with a plus. These also up here, it was a plus here. And these also have a plus. And so the idea now is if we do a kind of a more global majority vote, we can still decode. So we have 1 copy of this state with a negative sign here, and 2 copies of 0, 0, 0 plus 1, 1, 1 over root 2. So if we kind of can somehow do a majority vote on these triples, we can actually decode and recover the original state. So at least maybe we haven't yet said how we do this decoding, but we can at least see that we can identify which triple of qubits underwent a phase flip. And we can recover what the original phase was. So it at least seems like the shortcode is correcting us against both a bit flip and a phase flip.
Question.
Yes.
What kind of measurement are you doing here? You just measure all in like Z basis, or?
Yes, great question. That's exactly where we're going. So actually, do you or does anyone else see what sort of measurement we would want to do to, say, detect even just a bit flip? Like, is there some Pauli operator, some 9-qubit Pauli operator that we can measure that will tell us, for instance, if a bit flip occurred here?
You could use sigma x on 2 of the qubits and see if you get 1 or minus 1 back.
Oh, that's a great idea. So we could try to apply x tensor x to 2 of the qubits. Which 2? Maybe.
You would have to do 2 of them in the same. So the first 2, or the second and the third, or something right next to the other.
Great. Yeah, so this is almost exactly what we want to do. The one issue is if we tried to measure x tensor x, we would actually run into a slight issue. We're going to want to do z tensor z, but that's the exact right idea. Maybe I'll leave a measurement for now. So right, so this is the exact right intuition. If we want to correct, say, a bit flip, we essentially want to check kind of, are the first 2 bits equal to each other? Because in all the true code states, the first 2 qubits have the same value in the computational basis. Whereas after a bit flip, they have different values. It's like 1, 0 or 0, 1. But there's this weird duality thing going on where if you want to measure kind of in the standard basis, like if an X error occurred, we're actually going to need to measure a Pauli Z operator. And this was kind of this phenomenon going on down here, where we saw that to measure parities, like to measure x1 plus x2 to determine if it's even or odd, we need to measure z tensor z. So somehow if we want to correct a bit flip, like an X error, we need to measure a Pauli Z.
It's a completing question.
Yes.
So you keep saying to correct. You keep saying correct, but any measurement you do is going to collapse the state.
Yes.
So you're going to be able to even detect the error. Are you also able to correct it, or is there another step you're going to introduce?
Oh, thanks. Yeah. So yes, we should definitely get there. So essentially the first step is to detect the errors. And the idea is once we've detected a bit or a phase flip error, we can actually correct it just by applying the same flip again. So for instance, once we know that a bit flip, say, has occurred on the first qubit, if we just apply Pauli X to the first qubit, will recover the initial state. And the same for a Z error. So actually, if we can detect Pauli errors, we can always correct them just by applying them again. Yeah. So we will see how to correct arbitrary errors which aren't Pauli's too. It turns out that it's always sufficient to essentially have a way of correcting Pauli's, and then almost for free, we'll be able to correct arbitrary errors. We'll get there in a little bit.
Question.
Yes.
So far we have discussed like phase flip and phase flip, and I just wonder if we have like a non-unitary like error, so you get deep coherence, will this code help to protect like your state or no?
Yes, yeah, that's a great question. And we'll get there in, I'd say, a few minutes. So it turns out that, yeah, we'll essentially be able to collapse an arbitrary error into either like a combination of bit flips and phase flips, and then just correct either the bit flip or the phase flip by doing some measurements, and then just applying X's wherever we found a bit flip and Z's wherever we found a phase flip. But yeah, it's definitely a non-obvious thing. Yes.
And does this also retain the classical repetition thing where it can only correct for one bit flip error at a time? Or can it do multiple? As in like, it can only correct for, if there's a phase flip, it can only correct for your phase flip. But only one phase flip at a time, right? Because of the majority vote rule?
Yes, yeah, that's a great point. Yeah, the shortcode as we've defined it can only correct, and again, by correct, we really mean detect a single phase flip. So yeah, for instance, if we have two phase flips, we might fail to detect which ones happened. And that's also, eventually we'll want to get to codes that can correct more phase flips. Well, great, if there's no more questions.
Just wondering, but it can also detect a bit flip and phase flip if they happen together, right?
Yes. Oh, that's also, yes. Great point. So if any bit flip, any single bit flip happens, and any single phase flip happens, whether they're on the same qubit or different qubits, we'll be able to correct them, or detect them and then correct them. And the reasoning you can see is, say we're just trying to correct bit flips. A phase flip will change a sign in here, but it won't actually change like the values of these bits. It'll just kind of change the sign, the coefficients in front of our 000s and our 111s. So a phase flip really doesn't affect our bit flip correction procedure, because our bit flip correction procedure kind of just looks at whether we have zeros or ones in these states. So yeah, so the two are kind of independent of each other. No matter how many phase flip errors occur, we can always correct like one, or detect and then correct one bit flip error, and vice versa. Oh, I agree. So we just got a primer on this, how to decode. We saw we're going to want to measure some Pauli operators, and essentially to detect which errors are happening. And so we want to measure some Paulis. And we actually have a name for Paulis that we measure in order to detect and then correct errors. We call them stabilizers. And what is a stabilizer? A stabilizer is just an n-qubit Pauli operator, so a tensor product of Pauli operators. That preserves all the code states. Equivalently, it's an n-qubit Pauli operator where all the code states lie in the +1 eigenspace of this Pauli operator. So for instance, I think a few minutes ago we mentioned that kind of Z tensor Z, Z's acting on the first two qubits, might be a good thing to detect a bit flip in the shortcode. And indeed, if we even just go to the classical repetition code, so simpler than the shortcode, we can see that Z tensor Z then tensor identity on the third bit. If we apply this to 0, 0, 0, we get back 0, 0, 0, because z does nothing on zeros. And if we apply z tensor I to 1, 1, 1, we also get back 1, 1, 1, because z acting on this one it flips the sign to -1, but then z acting on this one also flips the sign, so we flip the sign twice, and that cancels out. So essentially z tensor I, which will actually denote z1, z2, to correspond to z's acting on the first two qubits, is a stabilizer of our code. It preserves all the code states. Can anyone tell me what is another stabilizer of this classical repetition code?
Z2, Z3.
Sorry?
I mean, you detected like the first two, the other two like Z2, Z3.
Yes. Great. Yes, so Z2, Z3. So I tensor Z, which we'll call Z2, Z3. It also has this property. So we have two stabilizers. Actually, these generate all of our stabilizers, because we could also take Z1, Z3. But Z1, Z3 is actually the product of Z1, Z2 and Z2, Z3. So essentially, Z1, Z2 and Z2, Z3 are essentially all the generators we need to essentially generate any of our stabilizers. And what this is going to mean is that actually, we'll see that if we measure just these two Paulis, we can detect and thereby correct any bit flip error happening on a repetition code. So let's just, oh yes.
So how did we say that there are only two stabilizers? Because there can be x1, x2, x3, and that's not the product of these two, right?
Sorry, what was?
So there can be another stabilizer based just on x, which is not the product of these existing stabilizers. How are we making the statement that we need only two stabilizers for encoding like these many number of qubits?
I see. So you're saying, right, we could have like Pauli X's and stabilizers.
Yeah, and like also, how many stabilizers do we need to define the stabilizer code?
Yeah, that's a great question. And it's going to turn out that so we'll also get there in a second. I agree, it's definitely not obvious. It's going to turn out that if we have an n qubit code, and we have a k message qubit, so we have a length k message encoded into n physical qubits, then we're going to need n minus k stabilizers to generate all the stabilizers and to define this code. So for instance, for the 3 qubit repetition code, n is 3, k equals 1, and so 3 minus 1 is 2. And so that's how we know once we find like 2 of these stabilizers, we're done. We'll kind of see an argument for why this is true later, but I think the high-level intuition is kind of each stabilizer it's essentially kind of cutting our space in half. It's giving us a constraint. And so once we have n minus k constraints, we get down to like a k qubit subspace of our n physical qubits. But yeah, maybe for now, for the repetition code, we'll just kind of see that these 2 stabilizers are enough, and later we'll see kind of this general formula. Oh, so I guess we can just quickly look at like exactly what happens when we measure Z1, Z2, or Z2, Z3 after an error. So let's say we measure both Z1, Z2, and Z2, Z3. And if we start with the initial state, just like 0, 0, 0, or 1, 1, 1, so a true code state, and we measure these stabilizers, we get outcome +1 for both of them. Because as we saw, like 0, 0, 0, and 1, 1, 1 lie in the +1 eigenspace of both of these stabilizer generators. If we instead have, say, 1, 0, 0, which is what happens when we apply an X error on the first qubit to 0, 0, 0. Then our Z1, Z2 measurement is now going to be -1, essentially because Z1, Z2 is measuring the parity. It's measuring the sum of the first two qubits mod 2, and that's 1 plus 0, which is just 1, so we get a -1. Z2, Z3 is still +1, because Z2, Z3 only looks at the last two qubits, and these aren't corrupted. Similarly, if we have an X error on the second qubit, so we'd have the state 0, 1, 0. Now we'll measure -1, -1, because essentially the parity of the first two bits, 0 plus 1 is 1, it's been flipped. And the second two bits, 1 plus 0, also have their parity flipped. And then if we have an X error on the third qubit, so we have 0, 0, 1, our syndrome, it's now kind of the reverse of the first case. So our syndrome will be +1 and -1. Because now the first two qubits are uncorrupted, so we still have +1. The second two qubits, their sum is 1, so we've detected a bit flip. Now, this pair of measurement outcomes, like +1, -1, or something like that, is called the syndrome. So the sequence of measurement, the sequence of stabilizer measurement outcomes is referred to as like the syndrome. These are our syndrome measurements. And the key point here for the classical repetition code is that the syndrome uniquely determines which bit was flipped. So you can see that these four syndromes, +1, +1, -1, +1, -1, -1, and +1, -1, they're all different, which means that after measuring these two stabilizer generators, we can essentially determine exactly which of the three bits was flipped. And once we've identified which bit was flipped, we just apply a Pauli X to that qubit, and we correct the error. So essentially, this is like a complete scheme for correcting a single bit flip. And I guess a quantum version of the 3-bit repetition code. Are there any questions for? Yes.
So, like you mentioned, this majority vote, that's just analogy, right? Because if we literally want to do the majority vote, we need to measure single Z basis, and
Yes.
that will destroy the QEC.
Yes, that's a great point. Thank you. So this is how we're essentially doing majority vote. Majority vote was just how we think of it classically, and this is exactly how we implement it quantumly. Oh, great. So there's still the question of phase flips. We've only seen how to correct bit flip errors. So phase flips are Z errors. And kind of what we've seen here is that if we have what we've seen here is that if we have a bit flip, an X error, we want to measure Z stabilizers. So that's this kind of like duality between X and Z that we saw before. And similarly, it's maybe not surprising that if we want to correct phase flips or Z errors, we actually want to measure X stabilizers. So there's always this slightly annoying duality where like we have the X side and the Z side, and we measure one to correct the other. But I can actually just write down, so the Z stabilizers, so we now need to go beyond the repetition code. We saw that the 3-bit repetition code won't correct, will not correct any phase errors. So we can go to the short code, which we expect to correct both bit and phase errors. And I think we saw earlier that one of the z stabilizers will be z1, z2. And in fact, if we recall from the shortcode, it essentially, the final step in creating a shortcode state was to perform an encoding into 3 copies of a classical repetition code. So essentially, we're going to have 3 copies of the classical repetition code z stabilizers. So we have z1, z2, z2, z3. I don't know if I still have the shortcode up. Z4, Z5, Z5, Z6, and Z7, Z8, Z8, Z9. I'll just write the code states again. So we encode 0 into 0, 0, 0, plus 1, 1, 1 over root 2, tensor 3 times, and 1, logical 1 is 0. So we can measure these z stabilizers and basically do the same error correction as before, but now we kind of have 3 copies of a classical repetition code. In the shortcode, we can correct a bit flip. To correct a phase flip, we want to measure some x stabilizers. Does anyone see or know what's a valid choice of an x stabilizer for the shortcode? So we want some sort of tensor product of Pauli x's that when we apply it to both this logical 0 state and this logical 1 state, we get back the same state.
X1, X2, X3.
X1, X2, X3. Oh, great. So let's try that. X1, X2, X3, say times logical 0. So maybe let's try logical 1. So when we flip all 3 bits in 0, 0, 0, minus 1, 1, 1, we'll get 1, 1, 1, minus 0, 0, 0. So we get 1, 1, 1, minus 0, 0, 0 over root 2. We've done that to the first 3, and then we have, on the other 2, we have the same thing but with a plus sign. And then we have again with a plus sign. Yep.
X1 through X6.
Yes, great. So X1 through X3 showed us actually a perfect example of what we're going to see in a second, which is an X logical operator, or yes. So we can see that X1 through X3, what it's doing is it's flipping the sign here. So essentially, we can take this sign and actually pull it out front. And it's flipped the sign of our state, which we'll exactly want to use operators of this form in a second. But X1 through X6 is exactly the way we fix this for now. So if we have X1, X2, X3, X4, X5, X6.
So just for 1 state, I think it should be negative in the sum.
Oh, sorry, which?
1, 1, 1 minus 0, 0, 0. And the same for the other state.
Logical 1, not 0.
Yeah.
Oh, thank you. Thanks. Yes, great catch. Sorry about that.
For the first one.
Oh, yeah. Right. So, thank you. Thank you. Yeah, so this was our logical 1 before we applied X1 through X6. Then once we applied X1 through X6, right, so we flip all our bits, so 0, 0, 0 goes to 1, 1, 1, and vice versa. And yeah, so here we've flipped the sign, because this is actually negative 0, 0, 0, minus 1, 1, 1 over root 2. So we picked up a negative sign here. We've also picked up a negative sign here. And these 2 negative signs cancel. So essentially we get back our logical 1 state. Great. So basically, this is a valid X stabilizer. And by basically the same reasoning, x4, x5, x6, x7, x8, x9 is also a valid X stabilizer. Essentially, now we're going to flip the sign in the middle 3 and in the last 3 qubits. We get 2 negative signs, and they cancel out. So these are our 2 X stabilizers. We have these 6 Z stabilizers. And it turns out that by measuring these 6 Z stabilizers and these 2 X stabilizers, we can detect and thereby correct any bit flip error, so any X error, or any phase flip error, any Z error. For the bit flips, it's basically the same as 3 copies of a repetition code. For the phase flips, essentially what's going to happen is once we measure x1 through x6, and then we measure x4 through x9, we'll essentially be able to figure out, kind of if a phase flip happened, which of these 3 triples of qubits it happened in. Essentially because a phase flip, for instance, if we have a phase flip on like this qubit here, the 4th qubit, that will just introduce a negative sign here in front of the 1, 1, 1. And then when we measure x1 through x6, that will now have the opposite outcome as before. So essentially we have kind of a meta version of a repetition code going on, where instead of measuring Z1, Z2, and Z2, Z3, we measure x1 through x6 and x4 through x9. But we'll see the same phenomenon going on where we have kind of 4 different syndromes depending on which triple of qubits received a phase flip. And we'll be able to detect and then correct the phase flip error. So to summarize, we have seen that for Shor's code, which is this encoding of a single message qubit into 9, or a single logical qubit into 9 physical qubits, we have 2 X stabilizers, 6 Z stabilizers, and measuring these, we can detect and thereby correct any X or any single qubit X or Z error. Yes?
Yeah, so for the Shor code, let's say in one case I have Z error at 1, and the other case I have Z error at, let's say, 3, and they all have the same syndrome, so how do I know like whether the Z exists?
Great. Yeah, that's a great point. I completely brushed that under the rug. So exactly. So the point is that if we have a Z flip on the first qubit, all that does is it introduces a negative sign here. If we have a Z flip on the 3rd qubit, also all that does is introduce a negative sign here. So essentially, Z flips on the 1st and 3rd qubits have the exact same action. So we don't know which one happened. The key point is that it actually doesn't matter because they do the same thing to our code state. So if we want to correct a Z flip on the 3rd qubit, we can actually just assume it was a Z flip on the 1st qubit and say apply another Z flip on the 1st qubit to correct it. So this is it's a special case of a phenomenon known as like degeneracy, where it's this weird thing where sometimes it actually doesn't matter which error occurred, because if two errors have the exact same action on the code space, then if you know that either one of the two errors occurred and you correct for that error, you're also implicitly covering the case where the other one happened. So yeah, so that's a great point. It's definitely a subtle point here. Yes.
Is it unique, or like we can break the like 2x stabilizers into say like 4 or other stabilizers and they can still correct it?
Or sorry,
I'm asking, like, is this like a unique set of x stabilizers which will correct the error, or we can have like a more elements in the say like x stabilizers which will correct the same?
oh, thanks. Yes, that's another great point. So yeah, so we've chosen two stabilizers here, and maybe I should be calling these stabilizer generators, because exactly this, there are other choices of valid stabilizers that will also work. For instance, one thing we could do is we could take the product of these two stabilizers, and we get x1, x2, x3, x7, x8, x9. And that's another valid stabilizer. In general, the product of two stabilizers is always a stabilizer, almost by definition, because if each of two stabilizers preserve the code space, then their product does too. And it turns out that kind of if we measure any set of like generating stabilizers, then that will suffice. So for instance, if we measure x1 through x6, and then we measure x1, x2, x3, x7, x8, x9. If we measure just these two and say, don't measure this stabilizer, that will also work. And the reason is that this stabilizer is the product of these two. So the syndrome we get, like the syndrome bit from measuring this stabilizer, would be the product of the measurement outcomes for these two stabilizers. So we can essentially deduce what the measurement would have been for this stabilizer by measuring these two and multiplying their outcomes. And so yeah, so in general, we really only need to measure some stabilizer generators, which is just enough so that we can uniquely identify the error. Yes.
Is that like for the same reason, like the indices, or are the indices not as material for like the z's? Like it goes 1, 2, 2, 3, and then you skip like it wasn't the next one isn't 3, 4, it's 4, 5. So that like the indices are immaterial, like in like a Lie algebra or something.
Yeah. So I see. So yeah. So there's definitely different valid choices here. The fact that we do Z1, Z2, Z2, Z3, and then we jump up to Z4, I would say that's not totally an arbitrary choice. I'd say that's more arising from the fact, like in this case, it's arising from the fact that we kind of have, by the way we define our encoding function, we have 3 groups of qubits. And within each triple, we have a classical repetition code. So if we try to go across 2 of these triples, we no longer really have a classical repetition code. So like in this case, kind of Z3, Z4 would not be a valid stabilizer. If you multiply these code states by Z3, Z4, you wouldn't get back the original code state. But yeah, definitely we can still multiply these stabilizers with each other and get additional stabilizers. Yes.
The n minus k result does not take into account the length of the errors, right? So if the length of the errors is 2, then you'd need more stabilized generators to correct for that, detect that.
I see. Sorry, maybe I was not clear with the n minus k. So the n minus k was for, or maybe tell me if this answers your question. So the n minus k was for essentially the number of stabilizers, the number of stabilizer generators, essentially the number of stabilizers we need to measure to correct as many errors as we can for the given code. So if the code maps a length k message, like k message qubits, into n physical qubits, so into a length n code word, then we can always find n minus k stabilizers, such that if we measure then, we can essentially multiply together these measurement outcomes and deduce what would be the measurement outcome from any stabilizer. If this code is a really good code, these n minus k stabilizers will allow us to correct a lot of errors. If it's a code like the short code, we may only be able to detect and then correct a single error. But kind of in both cases, we'll only need to measure n minus k stabilizers. well, if there's no other questions, then we have this. Oh, so these are essentially the parameters of the shortcode that we've seen. And there's one point which I said we would come back to, which we'll now come back to, which is non-Pauli errors. So what if we have a corruption on a single qubit, but it's something that's not just a bit or a phase flip? In full generality, we could imagine applying an arbitrary 2x2 matrix, so an arbitrary operator, E, that's just like E00, E01, E10, E11, some arbitrary 2x2 matrix to a given qubit. And this is still a single qubit error, so we want to be able to correct it. But it's not an X or a Z error. So how are we going to do this? It turns out that actually for once in our lives with quantum error correction, it's actually, the answer to this is like the easiest possible thing. It turns out that we can just do the exact same error correction as before, correct for X errors and correct for Z errors. And automatically, this error correction procedure will work to correct an arbitrary single qubit error. And the reasoning for this is, we can actually prove this in quite a simple manner in hindsight. The reason is that we can always express an E error as a linear combination of Pauli errors. So there exist some complex numbers, which we'll denote by like alphas. Alpha I times I, alpha X times X, plus alpha Y times Y, plus alpha Z times Z, where we recall that Y is I times X times Z. And essentially, we can write an arbitrary 2x2 matrix in this form as a linear combination of Pauli matrices along with the identity. You can actually check this for yourself that the 4 Pauli matrices we defined over there span the set of all 2x2 matrices, but maybe it shouldn't be too surprising because there's 4 degrees of freedom here, 4 entries of the matrix, and there's also 4 degrees of freedom here for these 4 coefficients. So maybe it's not surprising that every E can be expressed in this form. And what this means is that if we measure our X and Z stabilizers, we recall that the way we define measurement, it collapses the state into an eigenspace of the Paulis that we're measuring. And essentially, the eigenspaces of our X and Z stabilizers correspond to code states with Pauli errors applied to them. For instance, in all these cases where we had some code state and we applied a Pauli error, like even in the repetition code, if we have the 000 state and we apply a Pauli X error, the resulting state 110 lies in an eigenspace of both of our stabilizers. It lies in the -1 eigenspace of Z1, Z2, and the +1 eigenspace of Z2, Z3. And in general, if we take a code state and apply a Pauli error, we get something that lies in an eigenspace of the stabilizer, of all of our stabilizers. So essentially, this means that when we measure stabilizers, we'll project the erroneous state into some eigenspace of the stabilizers, which means we project it into we essentially project our arbitrary error into just some Pauli error. So we project this arbitrary error to a Pauli error. And then we've already seen how to correct Pauli errors by measuring our stabilizers. So for this reasoning, we can basically always just assume errors were some combination of X and Z's. We never need to worry about kind of arbitrary operators acting on our qubits. Are there any questions about this?
What about E is O0?
Sorry?
What about E is O0?
E is O0? Oh, all 0, I see. Right. So I guess there's also the constraint that in order for an error to occur, it has to be physically realizable. And kind of like we saw quantum mechanically, we can only perform unitaries. You can try to perform more general things called like quantum channels, but I guess the all zeros matrix isn't really it's not really something you can implement physically. So yeah, so that's a good point. We only really have to worry about errors that are things you could actually do to a qubit. And it's maybe easiest to think of that as just unitary matrices, which can't be L0. Yes, and then
What about like projecting out of the code space?
projecting out of the code space.
Yeah.
So like applying a projector or something?
Like you have like, let's say, a superconducting qubit and you excite it to like the third or fourth energy level, but you're only using the lowest two.
I see. So, I don't want to say anything about how to physically do that on a device, because I definitely am not the right person to answer that. But that may actually be strictly better than a Pauli error, because in a Pauli error, if you're using the bottom two energy levels, and you flip, say, the energy level 0 to 1, then you kind of don't know, is that 1 corrupted, or like, did we actually flip from a 0, or did we just start out at a 1? Whereas if you flip up to energy level 2, that's actually taking you like totally outside, so you already know that an error occurred. So in some cases, that can even be better, and you can treat that as an erasure. Essentially, you know an error occurred. But in terms of actually physically doing this, I'm not exactly sure.
Wouldn't that kind of be like a zero matrix error? Just everything left here to energy.
So I think,
I mean, it sort of is, you have to expand the space is the problem, and you're moving things outside of the space, so within the subspace of the 2x2, it may look like a sort of moving, hence the erasure channel.
yeah, you can think of it, as an erasure channel, which, I guess it's not exact, it's not just literally multiplying by 0, but. Yes.
If you have any non-unitary errors, then that just leads to like decoherence and you can't correct them.
Okay, so I guess this is kind of similar to this erasure channel issue. So, so we actually can correct it. What we can do is so abstractly what we can do is we can take a quantum channel and we can decompose it as a sum of operators which are all non-zero. Maybe I could write out the entire formalism, but maybe a simpler thing to do is like, say we have an erasure where we just totally lose a qubit. What we can actually do is just bring in a new qubit, just initialize to like the 0 state. And so we have the kind of map that sends an arbitrary qubit phi to just the 0 qubit. So it's not a unitary, but it is like a well-defined quantum channel. It's something we can do physically. And you can take this channel and kind of decompose it as a sum of operators, like a sum of kind of 2 to the n by 2 to the n matrices, where each of these matrices kind of only acts non-trivially on this qubit. And then we'll be able to decompose these operators as sums of i's, x's, y's, and z's. So somehow for like arbitrary channels you could write down, like things like decoherence, totally erasing a qubit, you can somehow always write down a decomposition of it into a sum of Paulis. So yeah, it's a little weird when you think about it, but somehow we can always do this decomposition. Exactly. Yes.
Well, in some talk, I think some people are also talking about measuring a Hadamard basis. Does that also imply there might be non-Pauli errors? This assumption that we are measuring in another basis.
I see. Yeah, so actually maybe I'll do one example here. So measuring in the Hadamard basis is, we can also think of just measuring in the standard basis, because if we do like apply Hadamards everywhere, just swap our basis around. Kind of in the dual picture, it's equivalent to measuring the standard basis. So maybe I'll give an example here and then we can go to the break. I'll give it here. So yeah, and hopefully this will answer some of these questions, because I agree this is like a very subtle point. So what if we have an arbitrary error, which was, or like some error that's just, like our error is just measure qubit 1. So this is something that's not a unitary. We could measure it in the standard or the Hadamard basis, but let's just think about it in the standard basis for now. So we saw that when we measure the qubit 1, so we do like a z measurement, that essentially either applies the projector onto the +1 eigenspace of z, which is just this matrix, or that applies the projection onto the -1 eigenspace of z. So essentially, if we do a z measurement, we, with some probability, apply this matrix. This is our error matrix. And with some probability, we apply, this is our error matrix. So our error is equal to like one of these two, this matrix or this matrix. So my claim was that we can decompose an arbitrary matrix as a sum of Pauli's. And indeed, we see that this projector here, just onto the 0 state, is equal to the identity plus Pauli z over 2. Whereas this projector down here equals the identity minus Pauli z over 2. You can just check that these identities hold, or that these equations hold. So essentially what this is saying is kind of, if our error is a projector, which is a non-unitary error, but it's something we can still physically implement, then either we're applying I plus z over 2 or I minus z over 2. And in both cases, we have a linear combination of Pauli's. In particular, if I plus z over 2 occurs, that essentially means that kind of in some part of the superposition, we've done nothing. And then to the rest of the superposition, we've applied a z-flip. So at most, we've applied a single phase flip. And here also, at most, we've applied a single phase flip. So in both cases, the fact that we can correct a phase flip means that we can correct this error. So essentially, this is saying we can correct any kind of single qubit measurement error as long as we can correct z errors.
Quick question. Does the sign between I and z matters, like in terms of possible errors?
Great. Oh yes, so this is also a great question. And the point here is that we essentially can forget about the sign after doing our syndrome measurement. Because let's say so this is our error. Then we measure our syndrome. That will collapse our error to either I or z. And then essentially there's no sign anymore because quantum states are only defined up to a phase. And similarly, if we measure our syndrome here, this will also collapse the error to either I or z. And our syndrome will tell us, did no error occur or did a phase error occur? So yeah, so somehow after doing the syndrome measurement, the sign goes away.
So intuitively, it seems that when you have a measurement error, you lose quantum information. So how is that correctable intuitively?
Right. So, you're saying we lose quantum information?
So intuitively, how is that correctable?
Oh yes. Yeah. So I'll answer this, and then we can go to the break. So this is actually a very nice conceptual point, which is that somehow we are losing quantum information. We can think of this as kind of pumping entropy out of the system. And so the key point is that when we perform these measurements, in some sense, like we need a supply of like fresh. We essentially need a sink, a way to like pump entropy out of the system, or we need to kind of use some energy. And essentially, what we're doing is we're taking all the errors. Kind of the errors can add information to the system, and we're pumping this information from the errors out of the system, without actually pumping the true information that we wanted to preserve out of the system. So Yeah, so at a high level, somehow it's like errors kind of add information, and our error correction only removes the information added by the errors. In this measurement, it's kind of only corrupting the information that was added by errors. It's not corrupting our underlying information that we want to protect. I think maybe we should go to the break, and if anyone has more questions, I can answer them.